So hello, I'm Rahul Kannan. So I'm going to talk about galaxy formation, including local radiation fields. I don't know if you want to do that, but I'll show you a model where we can boast that we have local radiation fields. So the first customary plot of why star formation is inefficient. So as usual, supernova feedback is invoked at the low mass for low mass galaxies, AGN feedback at the high mass end. Today I'll be concentrating on the third mechanism, decreasing the cooling rate onto the centers of the galaxies. And as Phil mentioned, that's what is called quenching. And also the main idea behind the talk was given by Sebastiano. So I'll show his plot first. So if you consider only collisional ionization equilibrium, then your cooling curve looks like this. You have a lot of cooling at 10 power 4 and 10 power 5 Kelvin. But if you include X-rays, soft X-rays from star formation events, then you can reduce the cooling all the way to this line where it is just Bremsstrahlung and then heating wave. So that's the idea. And Nick showed this in his last talk. So why do radiation fields decrease your cooling rate? So you're basically trying to solve the internal energy equation in your simulations, which has a heating minus cooling term, and the heating minus cooling term is a function of density, temperature, and your incident radiation fields. And your densities of each species is in turn also dependent upon the densities of the other species in the gas, and the temperature, and the incident radiation field. So what basically the radiation field does is that it can do two different stuff in the gas. Either it can photoionize the gas, thereby removing coolants. That is the most important. That is the most important effect, as we will see. Or it can photoheat the gas. So, when a photon photoionizes an atom, for example, then the amount of threshold energy of the ionization energy of the atom is of the photon is given to emit the electron from the atom, and the rest of the energy is given as thermal energy to the gas. So photoionization and photoheating are the two ways that the radiation field can affect your gas cooling rates. So this was the spectrum shown by Sebastiano as well. So we consider this the local radiation source. So this is the spectra of cumulative spectra of ONB stars plus the shock heated gas from stellar winds and supernovae. The assumption is that 5% of the mechanical energy is converted into thermal, and it is emitted in this spectrum. And this spectrum has been empirically matched to the X-ray luminosity of galaxies. So again, I show the plot here. So if you have just if you have a star formation rate of 1 and you have a density of the particle is 0.01 and solar metallicity, so it's a really high metallicity gas. If you have just stars from just O and B, so you have just UV radiation, then what you have is this thin line, so you do not really reduce cooling in this temperature range. But you have soft X-rays, then you can really reduce the cooling rate and change how your gas cools in your simulations. Where I deviate from Sebastiano's model is that I also include contribution from old stars. We heard a lot about it in the morning. So this is the Bruzol and Chalot single stellar population model showing the luminosity as a function of energy for different ages of the single stellar population. And you can see once you go above 100, about 200 megayears or so, your emission from this old stellar population becomes harder. Your luminosity at the hydrogen flux decreases, but your emission becomes harder. And this is mainly due to the post-AGB stars, which was also discussed in the morning. And the point here is that this flux, since all stars produce this flux, the luminosity scales as a mass of the whole stellar population. So if you have an elliptical galaxy which is 10 power 10 or 10 power 11 or 10 power 12 solar masses in mass, then because due to the contribution of these post-AGB all stars, you get a high luminosity in the far UV range, and there also the metallicity is lower, but you still decrease cooling by quite a lot. But you need a lot of all stars to produce this effect. So I'm a simulator. So first I'll just mention some attempts to include radiative transfer in recent years in simulations. So first to mention that most of the galaxy formation simulations use just the UV background to calculate the cooling rate in galaxies. But of course there are exceptions. There are some codes which do radiative transfer on the fly. But the point is, it's computationally very expensive, and you can probably study reionization and not more. The other end of the spectrum is you do radiative transfer in post-process. So you can probe the diagnostics, but you cannot really know what the effect on the dynamics of galaxy formation is due to this radiation field. So in order to implement this radiation field and also simulate the galaxy all the way to redshift 0, we have to make a couple of assumptions. We assume that the gas is optically thin, which makes the calculation of the radiative transfer a 1 by r squared problem. And then, since the simulations already do a 1 by r squared gravity problem, we tag this calculation onto the gravity tree. So we use the gravity tree in order to calculate the distance between the source and the sink, which makes this computation very efficient. And we also have to take care of the absorption, of course. So for that we do it very simply. So we assume that 95% of the Lyman limit frequencies is absorbed in the birth cocoon for young stars, but the soft X-rays, they do not see any absorption. For old stars, they are considered as field stars, and the escape fraction is unity. But I'll show you that in simulations that the old stars do not matter. So I implemented this in the hydrocode gasoline, and just to test if it works, I just take a particle at a particular temperature, 2 times 10 power 5 Kelvin. It is not coupled to any hydro or anything. So I just evolve its temperature as a function of time under different conditions of the radiation field. So if you see here, so you have just the Harder-Maddow at redshift 2, that's the blue line. The Harder-Maddow, then if you have a star formation rate of 1 solar mass per year, then it's the black 10 solar masses, 100 solar masses. So just by increasing the radiation field, the way your gas cools is different. And of course, if you increase the metallicity, then because there are more coolants, your gas will cool faster. But you can see that just by increasing the radiation field, you can change the way your gas cools in simulations. So I implemented, as I said, I implemented this in a galaxy formation code. So I did a simulation of a Milky Way type galaxy, halo mass of 6.5 times 10 power 11. It has all the feedback mechanisms, and I did 2 different runs. One where I have calculated the cooling only in the presence of only the Harder-Maddow. The other where I have the Harder-Maddow plus the local photoionization sources that I have just mentioned. And this is the result. So I look at the star formation rate as a function of time. The red line is just the Harder-Maddow. The blue is the Harder-Maddow plus the local photoionization sources. Up to a redshift of about 1, they both remain constant, but they start diverging. While the Harder-Maddow run keeps forming stars at a large rate, the local photoionization sources make the star formation rate to flatten off. And this is consistent with what Sebastiano showed, where at low redshifts is the maximum effect you get of this in low redshifts. To see why the star formation rates are different, I plot the temperature density phase space diagrams in both the simulations. So so this is the halo, the surrounding CGM or the hot halo of the galaxy, and this is the disk, and this is the hot and Madao round, this is the hot and Madao plus local sources. You can see that the halo is at a higher temperature here than here, and so what that means is your cooling rate and also the gas accretion from the halo to the disk decreases. The other effect you see is your disk is at a higher temperature because it sees a higher radiation field. But this is a secondary effect. I'll show you why. The primary effect is that you reduce the gas accretion from the halo to the disk. And you can see that here also. I plot the baryonic disk mass as a function of time in both cases, hard and hard plus local photonization sources. Again, up to redshift 2 or so, they are quite consistent with each other, the accretion rate. So the slope of these lines basically gives you the gas accretion rate onto the centers of the galaxies. So up to redshift 2 or so, they are quite consistent, but then after that they start diverging. And that's basically when your star formation rates also start diverging. And so because you reduce your gas accretion, because you reduce your fuel to the centers of the disks, you reduce your star formation as well.
So how do you find the baryonic disk mass?
I have a 20 kiloparsec by 10, and then I looked at this. It's just the center of the halo is how I consider as a disk. Okay, and you can see it in the other way. You can also see I have plotted dm dt delta t, that is the temperature histogram, as a function of temperature. So how much mass is in each temperature bin is what is plotted here. So if you have just the hot and Madao, then it's the red line, the green is the with local sources. What you can see is that it shifts the whole temperature regime. And it puts more gas in the high temperature regime and then removes the cold gas. But removes the cold gas, and this is what is important to change your star formation rates or regulate your star formation rates. And this is...
Our background is relevant to this a few tenths of Kelvin.
Sorry?
It's a few tenths of Kelvin. So this is cold gas. It's fully shielded. You cannot get to this temperature.
This one you mean?
Yes.
This, yeah, sure.
Why
Yes, as I said, I don't have self-shielding, so this part is not the most important. This is the part which is important.
How can you go to 20 Kelvin?
Sorry?
How can you go to this low temperature if there's no shielding?
He's saying if hard Madao is on, the gas should be at 10 to 4 K.
No, we have lower temperature metal cooling. Yeah, we have full metal cooling from cloud.
Still, that's a cosmological run. You have all the cloudy things.
But again, this part is not what is important. The part which is important is this, because you are increasing the halo temperature and you are reducing the gas accretion rate. And also you get flatter rotation curves. This is just mentioned. So as this conference is on quenching and quiescence of high mass galaxies, I also ran a very low resolution run of a high mass galaxy of 10 power 13 solar masses in halo mass. And then I compared the two runs. And the interesting thing is I form actually more stars if I include local photonization feedback. I have no exactly, I haven't analyzed the simulation much yet, but I think the point here is that you just just get rid of the cold gas and you do not change the halo temperature much. And so what you're basically doing is you are building external pressure. You are building pressure in the disk, and if there are some and so in order to maintain the equilibrium in a high pressure disk, the gas goes to higher densities and forms much more stars. And so again, so that's why I said affecting the disk is a secondary effect, because just by affecting the disk, you cannot really change the star formation rate of a galaxy. So now I'll talk about quite speculative stuff, which I've just looked at in the past week or so. So yesterday and today we heard a lot of talks about X-ray binaries and X-ray sources which can quench. So that's what is written here. So observationally, your high mass and low mass X-ray binaries are observed to have these scaling relations. So for high mass X-ray binaries, you have about 10 power 39 Hertz per second for every star formation rate of 1 solar mass per year. And low mass X-ray binaries are a bit higher, 10 power 40, if you have a all stellar population of 10 power 11 solar masses. And these are all observational constraints, mainly from Marek Gilfiner's group. And so what you can plot the spectra again. So this is the soft X-rays that I use. This is the post-AGB. This is the Hutton et al. Kirchhoff 0. And these two are the low mass and the high mass X-ray binaries. And then you can look at what they do. So I have a 10 power 12 solar mass halo, which is quite big. And then at a distance of just 3 kiloparsecs, this is just a test run. And then I have looked at how the cooling function changes for if you put in these high and low mass X-ray binaries. So if you have just the soft X-rays, that is the dotted line. If you add the high mass X-ray binaries in, it's the solid line. So high mass X-ray binaries do not do much above what we already have. But if you have low mass X-ray binaries, then you have just the post-AGB stars. That's the dotted line here. And then if you add in the low mass X-ray binaries, then you have quite a huge effect. But this is again at 3 kiloparsecs. If you go out to larger and larger distance, so red with red, brown with brown, and then you cannot see the difference dotted and blue and green lines. So up to about a distance of 10 kiloparsecs, the low mass X-ray binaries still produce some amount of difference. But again, this is hard X-ray, so it does not really couple really well with the galaxy, with the coolants, with the gas. Then another component that I've been looking at is the hot halo emission. So for here I have just considered a free emission or Gremsholin emission, where the emissivity is given by this one. And then I looked at two simulations from the MAGIC project that we have run here. One is this, the other, so one is a low mass, one is a high mass galaxy. So for the low mass galaxy, our X-ray luminosity by just using this is quite okay within the observational limits. X-ray luminosity versus stellar mass. And then for the high mass galaxy, we are here, which is also okay, but the point to make here is we are overcooling. So for a 10 power 13 solar mass halo, you expect a 10 power 11 stellar mass. So actually we are here, so we are overestimating the X-ray luminosity. It might be just that we are overcooling and we have a lot of hot gas there. It might have something to do with quenching as well. But if you do take this X-ray luminosity and just the free emission spectra, then this is what you get at different temperatures. So if you have old stellar population, which is post-AGB plus the low mass X-ray binaries, and then you compare it with what the hot halo does, which is the solid lines, you still have some amount of effect, but I do not know if that will change anything. So just to conclude, a nice method to include radiation field in cosmological simulations. So if you do a Milky Way mass galaxy, there is 67% reduction in the star formation rate, 40% reduction in the total stellar mass, and again, I will invoke this preventive feedback, so it stops gas accretion instead of ejecting gas out of the disk, and so it's a preventive feedback mechanism. And additionally, it does not work for high mass galaxies, I have shown. So additional radiation sources might have an impact. So high mass X-ray binaries I have shown are only a slight increment, so they might not work. Low mass X-ray binaries, they look promising, but we also need a soft X-ray component. Cooling radiation from a hot halo, it seems to have a very low impact even with boosted radiation fields, although I have to look further into this. Accreting white dwarfs, nobody knows. AGN, well, they certainly have a lot of energy in the hard, a lot of energy in the soft and hard X-rays, but they have a very low duty cycle, and as Vogelsberger showed, because of the very low duty cycle, the gas just cools back down when it shuts off. then you have to take into account this non-equilibrium cooling effects, which were shown by Ben Oppenheimer and Yorkshire. Thank you.
Questions? Rob?
It was just a very brief comment. So I don't think the fact that you're overcooling and you still get the right LX, or roughly the right LX, is a problem, because overcooling and feedback impact upon the same gas, the lowest entropy stuff. So you can actually end up removing a high LX gas, either by injecting it or by forming too many stars.
Okay. No, it's just, I found it strange that you're overcooling and you're over predicting the LX. So.
Well, it looks like a high LX.
Right, but the point, oh sorry. Point I'm trying to make is you're overcooled, so you have 10 power 12 solar masses, and then they are fine. But if you go by the Moster relation, then you should be 10 power 11, and then you're really above the observations. So for a halo mass, you're over. That's what I'm trying to.
It's almost like too much gases in there. So you have your hands up.
It seems your accretion rate in the Milky Way galaxy at redshift 0 was decreased by about 20%. So less. The accretion rate just from the plot.
Yeah.
Less than. Yeah, the next one.
Yeah.
No, this is star formation rate. So
yeah.
the accretion rate. Okay, yeah, it goes from 0.8 to 0.6.
That's the mass, not the accretion rate.
Okay. All right.
No, so the slope gives you the accretion rate, which is 7.5.
Which is 4. Okay, more. So what? So, and at the higher mass, you have a much smaller effect. So this seems to be a smaller effect than we might expect from Sebastiano's talk.
Yeah.
But you did put in the same radiation field, right?
That is, he's looking at lower mass galaxies. I'm looking at much higher mass galaxies. And this is in. Sorry?
Talking about the star formation rate, it stops when you reach the critical star formation rate for that particular galaxy. When it gets too massive, it gets too massive.
So he was talking about 3 times 10 power 11 at maximum. I'm talking about more like Milky Way.
So you're doing a simulation of that mass then?
Not right now, but we are thinking of.
That's a galaxy at the peak of the formation rate efficiency, so you expect that the formation rate is higher. So the reduction is due when it was less massive.
Yeah, and yeah, it's just to show even in Milky Way, this is a huge effect.
Thank you. Joel, did you still have a question?
Yeah, I was wondering if you or anyone else has included dust in any of the simulations, just because that's, until it gets floated away, it's very important coolant. In fact, it's the dominant coolant, and it's not going to be affected by photoionization.
Right, but it's at low temperatures, it's fine. And we want to affect the gas which is in the halo, not in the disk.
Well,
that is our.
Sees dust out to 500 kiloparsecs around galaxies, and if you adopt some gas density law, it's about a constant mass ratio per atom of gas. So it could be it seems to be quite plentiful.
I don't know if it will have such a big effect at those high.
So do you actually claim that the cooling in the simulated medium is due to gas?
Well, I tend to ignore dust actually, but
So
there
it's
are a lot of papers that tell you that.
There is more fractionally, but most of the cooling in the simulated medium is due to gas.
Yeah, you're suppressing the coolants in the gas, and that's the most
If there's a bit
important.
of gas, for example, it could be too much.
Now, the cooling due to dust, due to particles colliding with the dust and radiating energy away, is worked out for hot situations like supernova remnants to be the dominant cooling until the dust is gone.
But you're talking about the regime where the cooling time is much, much higher than this. He's talking about 10 to 5, 10 to 6 Kelvin or so. The cooling time is much shorter than in the highly Bremsstrahlung dominated regime.
So maybe following up on what Nick told us, so if you modify cooling and you want to sort of get at the same observation consequence, you have to also modify the star formation and feedback recipe.
Yes.
So in other words, are the solid galaxies consistent with the observations, or
So I'm not trying to match observations of galaxies. I'm just trying to see what the effect of radiation fields on cooling is.
Given a
We
fixed
already
star formation and a fixed feedback model, that
exactly. I'm just changing just the cooling recipe and just looking at you. The point is, we already know the feedback is strong, very strong. So this might help you to bring it down.
Okay, there's no more questions, so thank you, Rahul.